In the last two lectures, I had talked about the subject of cryptography, and let me sort of quickly review what we said. We said that encoding a message, which we will call as the plain text, to a code to be called as the cipher, and send such a coded message over a public channel such as a fiber optic channel or whatever you have, for being received and decrypted by a receiver. Now that is the whole crypto system that we are talking about. From encoding a normal plain text, then sending it, and it is being received in the coded form, and then finally this coded message being decrypted to the original form in which the message was sent is known as cryptography. As we mentioned last time, but we would like to reiterate it, there are four pillar stones or cornerstones of cryptography. Number one is there is a need for privacy, and the code should not be understandable by anyone other than the intended recipient. There should be integrity of data, that is, the data should not be corrupted during passage over public channel, and this would also imply that you protect your channel against either a malicious or a non-malicious eavesdropper who might be trying to tap that channel. The third and the fourth are non-repudiation, that is, a sender and the receiver should not be in a position to later on claim that they had either not sent it or not received it. And finally, there must be some method by which the sender is authenticated. The identity of the sender as well as that of the receiver are authenticated. We talked about RSA algorithm, and we said that RSA algorithm depends upon what we said as a trapdoor function, and which sort of tells you that there is a public key encryption for coding and sending data over the internet. And this also enables the sender to establish identity. The whole idea behind the trapdoor function was the function f is easy to calculate. In our case, it was just multiplication of two large integers. But the inverse problem of factorization is known to be a hard problem. And that is the basis of the RSA algorithm. With this, we will now try to see what differences, if any, will be made if we are to introduce quantum ideas into the science of cryptography. The entire subject started with a person, with a graduate student known as Stephen Weissner, who in 1960, in his graduate thesis, had suggested some very interesting idea, and I would call it as quantum money. The idea is this, that we use polarized light or single photons to store information, and this is done by having four different bases. And the basis meaning it could be vertical, horizontal along the x-axis, y-axis, let us say, or it could be diagonal basis making an angle of 45 degrees with the positive x-axis, or 135 degrees with the positive x-axis. Now, suppose in each currency note we embedded 20 light traps. These are light traps are tiny devices which capture and store single photon. Now, 20 devices would mean basically a huge possibility. Because each of the photons could be coded in one of the four options that I gave you, and so therefore if we have 20, it is 4 to the power 20, which is a trillion of possibilities. So therefore what do you do? So each bill picture tells you how it works. So in addition to the usual numbering schemes that you have, that a particular currency note has a number, the denominations and things like that, in each of these we have 20 light traps. The number could be vary, and in each of the 20 light traps I have a single photon which is encoded in one of these 24 bases. So obviously we have umpteen possibilities, as I said, 4 to the power 20 different possibilities. So there is no need for the code on one of the currency notes to be identical to that on another currency note. So therefore, the identification of the currency note and the basis which is used to store these 20 photons is kept in a database. So in case a doubt arises, then what one could always check against the database whether a particular currency note that has been brought in is genuine or not. Of course, you realize that this is a very expensive proposition and will obviously not work in reality. Just to check, let us say, the authenticity of maybe 1,000 rupee note, you will have to spend lot more. But that was not the point. The point is, this brought in the possibility of using quantum mechanics for verification purpose. Using quantum mechanics to code something confidentially. So that today when you go to a shop, people try to hold a currency note against either ultraviolet light or try to identify various symbols that might have been put in to see if they are in place. You will be simply able to check it against a database and find out whether the currency note is genuine or not. A duplication is out of question because the process of producing it is so expensive that even for the mint which makes it, it will become expensive. So therefore, an individual enterprise trying to duplicate it is out of question. So therefore, this is what it was. But this provided us with an idea. And this idea is based on the following, that it is not possible to make a copy of a random quantum state. We have talked about this no cloning theorem in detail. We have said that given an arbitrary quantum state, one cannot get an exact copy of this state. Second thing is this, that when you make a measurement, that itself will disturb the system, and that we have pointed out is because of uncertainty principle. Now, suppose that I have two people, Alice and Bob, who are trying to communicate something amongst themselves, and if they can be sure that there is no eavesdropper, which is certified by the fact that any eavesdropper would have disturbed a system by the process of measurement, then they can communicate through what we discussed as a one-time pad. Remember, the Burnham cipher or the one-time pad was a string of bits for which the identical copies are there with Alice and Bob, and this pad is to be used once and once only. So let us look at the various types of protocols which exist. We'll start with what is known as the BB84 protocol, which the nomenclature is because of two people who suggested it, Bennett and Russell, and 84 is because of 1984 in which this was given. Now, what this thing does is, they use a set of 4 polarizers and they use 2 bases. So Alice has a set of 2 polarizers, Bob has a set of 2 polarizers, and each one of them, they have decided among themselves that in order to encode a bit, if Alice is sending to Bob, in case of Alice, Alice will encode it in one of these 2 bases that she has got. And likewise, when Bob receives the bit, he will decode it using the same 2 bases. So let's look at what it means is this. So this, for example, is one of the situations. So this is a vertical basis in which a photon is being sent, and if that is the path axis of the polarizer, then the photons which come out of it, they have polarizations which are vertical as indicated. Now this one along with another basis which we call as the horizontal basis, in which case the path axis is horizontal and the photon that is coming out will have polarization which will be horizontal. So that is basis number 2. The number 3 basis is this, that I have a diagonal basis in which the path axis is at 45 degrees to the positive x axis and a photon that is coming out of it is also polarized in the direction that has been shown. And finally the one which is perpendicular to this is the one where the path axis makes 135 degrees with the positive x axis. So these are the 4 bases which Alice uses to encode a bit, and these will also be the basis in which Bob will be decoding it. And let's see how it works. Now basically Alice has 2 pairs of bases, horizontal vertical basis and the diagonal basis, which is one at 45 degrees, the other one at 135 degrees. So what Alice does is, she decides randomly, which could be done for example by tossing of a coin. So she tosses a coin. If she gets a head, she decides to use the horizontal vertical basis for encoding a photon. So supposing she has decided to use this basis, then she may use, for instance, the bit 0, the qubit 0 may be encoded as a horizontal one and qubit 1 may be encoded as a vertical one. And this is provided she is using what we have called as the horizontal vertical basis. Similarly, if she gets a tail for a coin toss, she will be using what we call as a diagonal basis, which using our usual notation, let's call it a plus minus basis. And in this case, she encodes a plus to indicate 0, the bit 0, and encodes a minus to indicate bit 1. So this is a photon polarized like this, and this is a photon which is polarized like this. So this is what happens. Now Bob receives this, but Bob has a problem, because if Bob knew exactly what basis Alice used for encoding a bit, then of course Bob would use the same basis and then he would be in a position to decode it easily. But that has a problem, because if these are publicly known, then an eavesdropper, let us say Eve, she will also be in a position to use that basis and interrupt it on the way. And so for example, if Alice is using a horizontal vertical basis and Eve also knows it, so Eve also aligns her polarizer accordingly, and when a bit comes, she gets the information and let that bit pass to Bob. So even though Bob has got exactly what Alice has sent, but so has Eve. So this is not desirable in the interest of secrecy of the problem, because in any public channel crypto system, we must always take care of the possibility that there was somebody who wanted to get this information on the way. Now, so what do they do? What they do is the following. Bob also decides to do a random job. So Bob will also tosses a coin. And let's say if he gets a head, he will also use a head horizontal vertical basis, and if he gets a tail, he will use a diagonal basis. Now what does it actually mean? Now suppose Alice has done this. So this is shown in the slide, but let me also illustrate it here so that we know what we are talking about. I will indicate I will indicate a horizontal vertical basis like this, and so this is my horizontal vertical basis and this is my diagonal basis. So the picture that I have shown you is the following. So what we are saying is this, that suppose Alice wants to send the following bits. So 1 0 0 1 1 0 0 0. Supposing she wants to send this, and she tosses a coin, and let us suppose she gets this, that. This is only for illustration purpose. So these are the Alice's bases. Now when Bob receives them, Bob also needs to decide which basis he will use. So oblivious of what Alice has used, Bob tosses a coin, and let us suppose Bob gets this, plus horizontal vertical, horizontal vertical, diagonal, diagonal, horizontal vertical, diagonal, horizontal vertical, and diagonal. Now let us look at what can happen. Now notice the bit received Now this is an example where both of them have used the same basis. So therefore, if Alice sent 1, Bob will also receive 1. We will come back to these where they do not agree. But here again there is an agreement, so therefore Bob will receive 0. The next agreement is here, so Bob will receive 0. So let me put tick marks over this to show that, and even this, to show that in these cases Bob's and Alice's bases were identical. Now what happens here? Now if you look at here, you find they have used different bases. Now when they use different bases, Alice could have sent anything, but Bob has an equal probability of measuring either a 0 or 1. And the reason is this. Supposing Alice has used a horizontal vertical basis to encode, let us say 0. But then 0 is equivalent to plus minus divided by square root of 2 in the diagonal basis. And so when Bob makes a measurement, he has equal probability of measuring plus, which is corresponds to bit 0, and minus, which corresponds to bit 1. So in these cases, this will be probabilistic. And let me just give you some idea. Supposing this is 1, this is 0, let's say this is 1, and this is 0. Now if you compare, what has happened is this. Here there is a 0, but we have a 1, so let me cross it out. Again here I have a 1 and a 0, so once again let me cross it out. But you notice here in these cases, this case and this case, even though the two bases did not agree, the bit sent by Alice is the same bit that was received by Bob, purely probabilistically. So these two are probabilistically correct. So let us look at what is actually happening. So assuming that there are large number of bits that are being sent, and since Alice is doing a random experiment of tossing a coin, suppose half the time Alice uses horizontal vertical basis and another half of the time she uses the diagonal basis. Now we assume that there is no eavesdropper in the problem. So firstly, when Bob's basis is the same as that of Alice, now that will happen 50% of the time. Now if 50% of the time the basis in which Bob measured happens to be the same as that of Alice, the bits Alice received will be the same as that Bob. The bits Alice sent will be the same as those which Bob received, and hence their bits will be identical. So that's 50%. So we are left with another 50% where Bob's and Alice's bases do not agree. But we have seen that probabilistically there is a possibility that even in half of those cases they would agree. In other words, the agreement between the bits sent by Alice and those received by Bob will be as much as 75%. The point is that though they would agree 75% of the time, only for 50% of the time they have used the same basis. Now what Alice does is to she uses a classical channel, and she will not announce what bits she used, but what she will announce is that what are the bases she used in sequence to Bob. For example, in the example that I gave you, after the transmission is over, Alice will make an announcement over a public channel such as a telephone or whatever. She will simply say horizontal, vertical, diagonal, diagonal, horizontal, vertical, diagonal, horizontal, vertical, horizontal, vertical, diagonal. This is all the information she makes it to the public. She does not quite say what are the bits that she has sent. Now when Bob receives it, he takes the following action. He removes all those where Alice's bits and Alice's basis and his basis of measurement did not agree. What it implies is he is going to throw away half of those cases where there was a probabilistic agreement between the bits that Alice said and the bits that Bob received. These two he will throw away in spite of the fact that had he kept them, they would have been the same. But this is done in order to achieve a certain amount of uniformity, because Bob has no idea which bits would have agreed randomly. Now once Bob has thrown this away, you have essentially 50% of the bits which Alice sent, and Bob has an identical copy of those bits. So now what we need to do is this, that this is fine, assuming that Bob's and Alice, they are not being intervened by a third party whom we will call as the Eve, who is trying to get information from the public channel. Now, what makes this problem a little more challenging now is this. Let us suppose there is an Eve in the system. What can Eve do? Now, Eve has a possibility of tapping what Alice sent, keep that and make an identical copy of it and send it to Bob. Now this is prohibited by the no cloning theorem. So what will be done is the following, that we would somehow be alerted that there is somebody in the system who has made a process of measurement. And let's see what happens when such a thing happens. So let us now introduce into our system the presence of Eve. See, if there were no Eve, which Bob and Alice can ascertain by certain process, then they can communicate, assuming that the bits of strings which they have agreement on, that becomes their secret code. Now at this stage, we have reproduced the same diagram in the presence of the Eve. But now there is a difference. There are situations where now Eve, not knowing what to do, also uses a coin toss method, because she knows Alice and Bob are using either a horizontal vertical basis or a diagonal basis. And based on that, she makes a measurement and passes the bit to Bob. Now, what will happen? How will this affect our Bob's reading of the whole thing is what we will take up in the next lecture.